Okay. That's perfect. So thank you everyone for being here for the Cryptanalysis of Cryptography. We'll have 4 talks today, and the first talk will be given by Romora, and he will explain us a new approach based on quadratic form to attack the packet distributions. So Romora, the project.
Okay, so thank you for the introduction. And yeah, today I'm going to present some results to analyze the crypto system, and in particular to distinguish the underlying code, or proper code, and potentially report security. This is a joint work with Alan Kudrow and joint activation. So what is the mechanism of the system? Well, this is a public key encryption scheme that enjoys both fast encryption and decryption, while the main drawback is that the public key size is very large. It's also one of the oldest public key schemes still alive, because it's basically as old as RSA. But differently from RSA, it is also believed to be quantum resistant. This is mirrored in NIST post-quantum standardization process, where Cryptanalysis is currently a finalist at the 3rd round. It is considered by many to be ready for standardization. So in particular, it belongs to the family of code-based cryptography, so it relies on the recording the linear code. But in order to decrypt the messages efficiently, one needs to choose a code from a specific family that has an efficient decoder. And both the NIST candidate and the original proposal by Mercedes use Gopher codes. Now, this is really a crucial point because during the years, there have been many attempts to replace Gopher codes with other families, but almost all of them have been broken. I can mention some families that are related with Gopher codes, but not the same, like generalized reason codes or algebraic geometry codes on one hand, and on the other, structured versions of Gopher codes, like when we add a quasi-cyclic or a quasi-layeric structure, or we take but for all of these, there have been efficient structural attacks. But interestingly enough, if one just takes a random Gopher code, then it's not known how to exploit its algebraic features for cryptanalysis. So what is the reason why Gopher codes turned out to be such a good candidate for the mechanism scheme is not a coincidence. Actually, they share a lot of properties in common with random codes. For instance, they symptomatically mean the Gilbert-Basham now. They have essentially the same weight distribution and also give a repetition proof. So for all these reasons, and actually many others, the Gopher distinguishing problem, we just asked to determine whether a generator matrix comes from a Gopher code or a value 1, has been considered difficult for a long time, and has been used to devise security proofs for the mechanism framework. However, it was actually shown in this 2011 paper that the Harm's assumption, this problem, is false, at least in the regime where the code weight is high enough. Because in this case, there exists a polynomial time distinguisher on Gopher codes. Now, this distinguisher does not apply to classic cryptanalysis because the rates used there are much lower than the distinguisher threshold. But still, it is somehow a breakthrough because it's very important to understand which parameters are suitable, which are not, to instantiate cryptanalysis. And also, it does apply to CFS digital signature, which it requires the use of high-rate binary Gopher codes. So what is the picture of cryptanalysis over the mechanism scheme? Well, if we define S as the codimension, so the difference between the length and the dimension K, then in the usual setting where we let the parameters going with fixed weight, so when M grows linearly with S, the two main families of attacks, key recovery attacks and message recovery attacks, have both exponential complexity. However, the exponent, the coefficient at the exponent for message recovery attacks is much smaller. And that is why when designing parameter, one just needs to thwart the threat of message recovery attacks. If instead we take the generate parameters when the length n grows at least quadratically with respect to the codimension, then these two families of attacks still have exponential complexity in the codimension. However, this is exactly the regime where the older the distinguisher that I mentioned applies. And our first contribution was to derive a key recovery attack on Gopher codes, an efficient one, polynomial time, in this regime, under the additional condition that the field size Q is strictly larger than R+1, where R is the Gopher. So unfortunately, it does not apply to binary Gopher codes, but still, it's the very first attack on Gopher codes without additional structure. And our second contribution is a sort of generalization of the previous distinguisher, because now even when we are in a setting where n grows as our alpha best is between 1 and 2, so for a range of parameters that were not distinguishable before, we now have a new distinguisher that runs inside exponential time, and that is the complexity. So not only beats previous key recovery strategies, but it's also asymptotically better than any message recovery. And so for the rest of the talk, I try to give an overview of this contribution. So now we really need to go into delve into details, and so we need to understand what is a code. This is typically defined as a subfield of a code of a JavaScript code. So it's defined by ground field here. However, for our purposes, it will be beneficial to give an alternative definition, makes use of the notion of extension of a code of a field extension. So what is it? Just take a code, an F2 linear code C, so all these code words, but then we take the linear combinations of them over the extension. So if we apply this construction, we can give an alternate definition of alternate code, and we will see that its relation with proper code. So we define an integer, positive integer r, and two vectors x and y, both of them n defined over t to the n. And so an alternate code of degree r with support x and multiplier y is defined as the code was dual in the extension field is spanned by this basis polygraphic A, where we have all the vectors of the form y times some power of x between 0 and r minus 1. And then for each of these elements, we also take all the n images for the Frobenius of the matrix. But okay, this is an alternate code. What is a Agoppa code? Well, an Agoppa code is nothing but an alternate code where x and y are related. In particular, yi is defined as the inverse of gamma evaluated in xi for a fixed polynomial gamma for a polynomial of the weight for the r. So all what you need to remember from now on, understand Agoppa codes and our distinguisher, is this definition of calligraphic A, which is what we will call canonical basis. And of course, it's a secret one, meaning that the attacker does not have access to it, because otherwise, x and y that are the secret would be. Okay, so now our work starts from the very simple observation that there exist quadratic relationships in the canonical basis. And I give you an example. So if we take the component-wise product of y and x squared y, this is equal to the component-wise square of x squared. So this is a trivial identity, and in the same way we have many others. But more in general, and for generic basis B, you can write a quadratic relationship as in the orange box. So we have component-wise product of elements in the basis, Bi and Bj. Then we take some coefficient Cij, and we want the sum over Ij to be equal to 0. Now, we can associate a quadratic relationship with a quadratic form in the trivial way. So the coefficient Cij becomes the coefficient for Xij. And then we can define a matrix MC such that for all x and y, that equation is satisfied. So x and y transpose is equal to the polar form of Q. And the matrix n that comes out from this condition is defined in the following way. So it's a symmetric matrix where outside the diagonal Mij is equal to Cij, while on the diagonal Mii is equal to Ci. So now we collect all the matrices coming from any possible quadratic relationship. So we have a set that has a vector space structure, so it's really a matrix code containing the space of symmetric matrices of size k, and that we call sigma of k. So this is the basic construction that would be useful. So let us come back to our previous example, to our previous identity. The matrix MC that corresponds to that identity is that MC that is 0 outside the top left split and free block. And so basically that's rank 3, not characteristic, and actually just characteristic 2, because the minus 2 on the diagonal becomes 0. So this means that sigma of A contains matrices of very low rank. And if you are familiar with code-based in rank metric, well, this typically suggests that something could be done in that. But okay, one could argue that the attacker does not have access to the basis A, but rather to another public basis B. And And well, yeah, that is true. However, we can prove that if A and B are two different bases for a same code, then CMAT of A and CMAT of B are congruent codes, meaning that there exists an irreducible P such that CMAT of A is equal to difference codes and CMAT of B density. And actually, this is exactly the transition matrix between A and B. So as a corollary, we have that the weight distribution of CMAT of A and CMAT of B is the same if computed with respect to parameter 3. And of course, the dimension is also invariant. But this implies that CMAT of B contains low rank matrices as well. So even if we cannot predict the structure of low rank matrices in CMAT of B, we still know that they must exist. So we may wonder if this is something really unusual or something that also happens for a random R with a basis B. And we can actually show that if the rate of R is at least 2/3, then we do not expect to have low rank matrices in CMAT of B unless we have some negligible probability. And look at classic Michaelis rates, and this is the last column in the table. You can see that the rate is always larger than 2/3. So it means that, okay, we construct CMAT of B, and if we are able to either find low rank matrices or prove that they do not exist, then we have a distinguisher that, differently from the previous one, works for fixed rates and for real Michaelis quantities. Now, the problem of finding low rank matrices is known as mean rank problem. So we are given a set of matrices and we want to find a linear combination that is an element of rank as upper bounded by some given value t. And here we really have a symmetric variant of this problem. And for this problem, there exist several modelings. So the modelings are quite advanced, but the simplest way to model this is just to require that all the minors of size t plus 1 must vanish. So if we now focus on the case of characteristic 2, where the target rank is 2, this means that we obtain a set of polynomial equations of equilibrium. But we can actually exploit a very particular structure of our code to improve the modeling, because symmetric matrices with 0 on the diagonal in characteristic 2 are also skew-symmetric. And we know that for skew-symmetric submatrices of even size, the determinant is actually the square of a polynomial called the function. And here you can see an example for a 4 times 4. So we can replace the minor modeling with the modeling defined by the minor, the ideal of minors, with the Pfaffian ideal for one is defined there, and it contains all these Pfaffians, all these degree 2 polynomials. And so this means that we have described the same variety, the same set of solutions, by using quadratic polynomials instead of cubic ones. This is clearly an advantage because, in general, when one wants to solve a polynomial system, for instance, with global basis techniques, the lower the degree of equations involved, the better. So our modeling appears as follows. The variables are the entries of our formal matrix M. And then we have these Pfaffian equations and additional linear relationships coming from the fact that, expressing the fact that we are looking for low rank matrices, not in the whole space of skew-symmetric matrices, but just in a top space that is our matrix. And we can count the number of such equations. So now we want to understand the complexity of solving such a system. And a very useful tool in algebraic analysis is the Hilbert series. So just recall very quickly that for a homogeneous polynomial ideal I, the Hilbert function at some degree d is defined as the difference between the vector space generated by degree d monomials and the vector space generated, the dimension of the vector space generated by degree d polynomials in I. The Hilbert series is just the generating series of the Hilbert function. So we want to study the Hilbert series for our ideal to do that. Now, if we start our construction from an alpha of code, then the analysis is pretty difficult because all the equations involved are non-random. And so we cannot rely on known results, generic results. But still we can trivially upper bound the Hilbert function by just saying that for any d, the Hilbert function evaluated at d is strictly positive. This is just because we know that non-trivial solutions must exist. If instead we start from a random code, then okay, Pfaffian equations are still non-random, but the linear equations become random. And so the analysis becomes easy if we know in advance how the quadratic equations behave alone. Luckily, this result is known in commutative algebra. So in other words, it is known that Hilbert series of the generic fucking ideal is given in this theorem. And based on this formula, we can obtain a heuristic formula for our ideal Q plus, taking into account the effect of random linear equations that is given here and that has been verified experimentally. But okay, why do we need why do we care about the Hilbert series in the random case? Well, because this gives us a distinguisher in the following way. So if we define this zero as the minimum value at which the Hilbert function becomes zero in the random case, then it is enough to compute the Hilbert function at zero to have a distinguisher. Because if it evaluates to zero, then it means that it comes from a random code. If instead it is strictly positive, then it, with high probability, will come from an alternate or a buffer code. So from our experiments, the D0 grows asymptotically as S squared divided by K. And so by plugging in the complexity of the Hilbert function, of computing the Hilbert function at some degree and doing the math, we obtain what I've anticipated, this complexity that depends on alpha, where alpha is such that n grows as S to the alpha. And again, when alpha is between 1 and 2, we have a sub-exponential alpha. So to summarize, we introduced a new approach based on quadratic forms and on the rank invariant to model the distinguishing problem. And we model it in particular for the case of characteristic Q by using the Fatian ideal. And by studying the Hilbert series of this ideal, we derive an upper bound of the complexity of the distinguisher that ranges smoothly between polynomial and exponential in a new regime of parameters that were not distinguishable before. The other contribution was an efficient attack on some parameters that were already distinguishable with this distinguisher. So basically, now we can break any generic alternate code that is in the high rate regime, regardless of the field size and the degree. And for the first time, we also managed to create some distinguishable Gopher codes, namely those for which the Gopher polynomial degree R is strictly smaller than the -1. So what is left open? Well, of course, having a deeper analysis of the Hilbert function in the case of a code could give a better bound on the complexity of the distinguisher itself, and could also be useful in order to understand the complexity of solving the polynomial system, which could be useful for the even more interesting task of transforming the distinguisher into an arc. In the same way as after several years, we managed to transform the old distinguisher into an arc for the same parameters. So that's it for me.
Are there any questions?
I wonder, so is the your form user in your type of defined or not? In your type is the political form. So is this political form or positive or non-positive?
But on finite field, I'm not sure there is a definition of you mean for the typically this is defined over the there's not a notion of positive or negative or
And also,
not really, because this is not a generic attack on code-based cryptography, but just on the mechanism scheme, meaning that it's an attack on the specific family that is used as part of a code. So it's something that is not reflected in lattice-based cryptography. You don't have like the analog something very specific, not only to code-based cryptography, but really
Are there any other questions for our speaker? So maybe I have one. The idea you presented is really say based on the fact that you can exploit the cryptography because you're looking at the consistency. Do you have ideas, or maybe it's on the paper, I don't know, on how to deal with the current test, not current test?
Yeah, I mean, one could still use one could still use the minor modeling, and the basic idea works in the same way. So if you solve the polynomial system associated with this idea, you still are able to distinguish or solve the polynomial system and find low-rank matrices. We chose to focus on the case of characteristic 2 because this is a more this is the most important one because mechanism is usually based on binary copper codes, scaling for CFS. And also because in this case we have a very nice analysis of the Hitler series. So if you want to move to characteristic different from 2, you just have to understand the analysis, but this may change the complexity of the distinguisher, but still the idea remains the same and work.
No other questions? Thank our speaker once again. For our technical presentation, we're happy to have Jonas to explain us how to solve the integrable problem in the case of C-side and C-sure. The automated version of the process. Jonas, the board is yours.
Thank you. Right. So this is joint work with my colleague Julian, who's also giving a talk in this session. And let me start this talk by motivating the number problem. And for this, so this is the notion of a group action. Very briefly, in a group action, we have a fact and a group G, as well as an applicant that takes a group element, a set element. And this framework is very general, so a lot of things because we can pass into this framework, right? For example, differentiation in binary groups, scalar multiplication on a different curve, as well as social extended group. So in cryptography, they appear everywhere, either explicitly or implicitly. And if you have a commutative group action, then what you can do is you can go a very easy change with this essentially with the decoupling. So for this, Alice and Bob will choose a secret group element with A and B. They then compute the action of the group element on some set X, probably known. And then they will just change the results, and in the end, they can share the which are called XAB. Now, of course, in theory, we are concerned about the security of these kind of changes, right? We have security reductions for them. However, in practice, they could also be. So let's assume now that there's an attack B that attacks other divides, and by a fractional attack, somehow able to extract some of the most significant bits of their shared the question now is, can we recover the remaining least significant bits? If so, how many bits does she need? And I want to stress here that Eve attacks shared element and not Alice's. Now this is called the hidden number problem and can be defined the way given elements involve public elements as well as an access to an oracle that takes into any set element of y, so actually any public y, and then computes the key exchange with Alice, so if Alice is 50, and gives back the most significant say the k most. And of course, it asks to recover the shared number. Now, this problem has been looked at in many contexts before, right? So, for example, in the 90 case of the star, as well as in the elliptic curve economics, and also in the post-quantum SADH, although SADH is technically not a reflection. However, in the literature, there are two popular post-quantum systems called C7, which are also common in some. However, there has not been any result on it. And this is what we try to solve. So our first contribution was that we solved the number of C-set, where in the C-set case, we need an order voltage difference 54% of the T, and then we can recover the remaining 6%. So in this picture here, the red part is the one that we heard with laser, and the blue part is the one that we heard. And in C-set, interestingly, although they are very related, we need that, and we can only recover. So the recovery is only us. And I will explain what that is. Now, what's nice about this recovery is that it works with any continuous block, like this. So imagine this blue part here being shifted to the left. So as long as it's continuous and doesn't overlap borders. And also in contrast to many other results, we only need 3 oracle traces in our recovery. Whereas, for example, in the elliptic curve setting or anti-Common setting, you would need an amount of trace that is somewhat dependent on the system. Now, internally, the recovery uses the optimal method, and the second contribution actually relates to the problem, because we were able to completely automate the code. Where in previous result, the optimal method required a lot of manual work, and in particular, that one simulation function that can be quite a lot of effort, but we observed that it can be significant to the problem with that. And this problem can be solved. And the last thing we provide. So let me now introduce CSET and CSET in more detail. And as with any progression, we have to talk about 3 main things. We have to talk about the sets, the group, and the set is pretty easy to explain. The set contains elliptic curves in one form, which are elliptic curves that elliptic sets, and they are essentially defined by one single term n, which is the mononomial coefficient, and it's essentially infinite. And so whenever Alice and Bob exchange elements, they actually just exchange the mononomial coefficient because it defines. So in this talk, I will use mononomial curves and mononomial. Now, what about the group? Well, the group I actually want to introduce. Let me just tell you that there is an actual group that is mononomial group. And the only thing that we need to know is that this group is generated by generators, G1 to Gn. And these currently represent functions. What we think is that each of these generators takes one elliptic curve. Right, so essentially these take one mononomial coefficient, and the action actually can be described by polynomial, shows like this. To be fair, in practice we wouldn't use these polynomials, that's more otherwise we would them. But at least in theory we can write all these polynomials and get the feature. And for me this is actually really convenient because you can see multiple things now. First of all, you can see that one mononomial coefficient is mapped to another mononomial coefficient, right? And what you can also observe is that in C side we have one generated class, and in C sub. This is due to something nice, right? And I guess it's different. And also what you can observe is that these formulas get more complicated. Again, I won't explain what these additional variables here are. You can compute them, and there is a way to evaluate these polynomials, but we don't. And lastly, just to complete the picture, an actual peak tensor don't do, with multiple generators. And so let's not look at the strategy of how to solve the hidden number problem. And I restated the hidden number problem here again. But now with the updated notation. So the whole recovery is based on the following observation that if we fix a generator, then the repeated action of this generator on the side. And of course, the length of the cycle depends on the order of the and for simplicity, let's just assume that the generator has to. I mean, this is not usually the case because the multiple destroying orbits cycles. But again, for simplicity at the start, let's just assume that this cycle here contains all the. So what this means is that Alex involves public discourse at the side. And if I now query the oracle on Gauss curve, then I get the most significant bit of the shared code of the sum on the side. But I can then if I now query the oracle again, then I get the most significant bit of this right neighbor of the shared term as well. This is essentially due to commutativity. Of course, we can also do the same with the net neighbor, where now we need to use the element the item minus one. So essentially, by using commutativity, we can explore the neighborhood of this curve here. And the hope is that this additional information tells us what the limit of EA. Right. So how can we make use of this? I've drawn the situation here again. Right? So and we have this left and right neighbor, and they are connected by some generated time. So what can we say about the relationship? Well, remember these formulas I gave you a couple of seconds before? They tell us how one of them is with the other one if we know that they are related by. This gives us a way to express the neighborhoods of the neighborhood. We'll prime to the other side, and then have an equation which is these two Montgomery coefficients are connected. And that's exactly what we want to do, right? So we can now just rearrange these formulas and square them, and then we get this system of equations. Maybe I should go back, but and it mentioned that of course we want to stick to those equations that are the same, right? So essentially we should stick to those that have the smallest two small terms. These get more complicated, and we want the system of equations that's simplified. So in the Caesar case, it would be the general one, right? That's the simple formula, and then we get this kind of thing. And of course, we can now try to solve the system. However, in the actual hidden number problem, we get even more, right? So we want, and here we can actually follow the prediction that if I get the most significant coefficient, then I can write it like this. So I have the most significant bits shifted by a couple of more plus the unknown basically. If I now plug in this equation into this system of equations, what I then get is a system that has a small solution in the missing bits of this question. Well, the whole Montgomery coefficient should be a root of this system of equations. But I already know the most, so the only variable that's left are the unknown these. And as integers, these are small. Right. And well, that's the main observation. So we could try to solve this system. And well, what about the CSAT case? In CSAT, we actually have a very similar situation. Here we only have the generated computer. But also remember that the recovery in CSAT was much better. these are actually a very problem that all generators gives us an and this is very specific to the Susa case, it's not a clear search. And what this means now is that if I use this element time, I get an additional relation between that. And furthermore, there is a nice theorem by Newton to show that the action of this element is very easy. So the action could be. So what this means now is that I get a system of equations that has three equations and also the equations are conceptually simple. So the degree is smaller, total degree is 2 and here it's 3. And also the shape of this polynomial. And in the last step, I now can do the same trick as before, where I can use the form of vectors and then get a system of equations in that. And for this, I can use. So in the coupled method, you try to solve a coupled problem. There you're getting polynomials in k variables, as well as some bounds, capital X1, which is k, and some modulo p. And what you want to find is you want to find all the small roots of these polynomials over p, where the root should not be bigger than these bounds. That's the main idea, but in most of the cases, you actually don't get this bound. So essentially, you want to find those the largest bound that allows for an efficient. That's the case in graph as well. We not only have to find the root, but we also have to find some bounds that. So what's the strategy in solving this? So very briefly, we would pick an integer and then define shift polynomials. These essentially are polynomials that have the same root, but now over a bigger number. So essentially, you get additional relations that should also be satisfied by the solution. And later on, actually, you would let n go to infinity and then let it on top of the case. Now, in fact, because there are a lot of these shift polynomials, would then select a subset of these all the time. And from the subset, we would then construct a map. And the last study, which and the lattice reduction to find the small one. Of course, this is a bit high level, but I hope it's fine. The main takeaway here is actually that the performance of this strongly depends on the choice we have. So what I mean by this is that depending on what subset path we choose, we can either have a larger bounds or smaller. And I guess there are now two problems that most of the coupled test results try to overcome. First of all, how do we select these shift polynomials, and subsequently, what's the largest bound that still allows for an efficient recovery? And there's actually no clear strategy for solving either of these questions. In this work, however, we observed that both of these questions can be solved automatically. And in the first case, we observed that this subset actually only depends on a single shift. The other ones can be selected automatically. And so what this means is that you just need to select one shift polynomial, and then depending on how good this choice was, you get either better or worse. And actually, there exists an canonical candidate for this single shift polynomial that might not give the best results or the optimal results, but still a good starting point. And lastly, the second problem can be solved potentially by using polynomial interpolation. Remember that it says that we are interested in the asymptotic cases with that go to infinity. And essentially, we can now apply polynomial interpolation as long as we assume that these bounds behave as polynomials. So that's all I want to say, and now I have to take questions.
Thank you. I have one question. Is can the cobblesmith solve the normal and cobblesmith in for CSI here to CSI function?
So what I understood is that can you use the automatic couplesmith for the original hidden number problem?
Yes.
I guess that in the original hidden number problem, you wouldn't use the couplesmith method, at least in the automatic setting. Overlaid recurs, you would use the couplesmith method, and there, I guess.
So what is the condition of the cobblesmith solve the number? Yes.
What do you mean?
So,
How do we select this optimal chart? How does it I guess you want to set the components here as large as possible. So that is sum to sum. I left the detail out.
Can you approach to equally because as I understand your work, your attack work for the continuous block, and for some cases the leaky bit equate.
No, you can't set. So it has to be a continuous block. But otherwise, the amount of variables that you get increases by essentially the amount of big blocks.
So then you go use the equate case with
another word.
So
Oh. Okay, sorry.
is
This one.
yeah. I mean it's X1 opens L1 to LK to large, so is also find the how much
Did you catch the first part?
I mean, if the X1 to XK are very large, I think that is enough to cover our. But if X1 to XK are not large enough, so for example, our X1 to XK are small, so I think that will be enough.
So this couplesmith problem gets easier the smaller the bounds are. Essentially, if the bounds are, let's say, all set to 1, then you're going to calculate problem with D. What you want to do is you want to maximize to make it as large as possible. But then, I guess, you recover more of these significant. These bounds essentially tell us how many most significant bits we need to get from this order. Because if we go back one more time, the bound tells us how large this unknown variable can be. It's large, and of course this one is small. That's what we get that from the order. And this is what we want to maximize. Of course, if the order returns 99% of the key, then order.
Fixed.
Correct?
I mean, the left side is fixed.
This one?
Yeah.
So this is the thing we want to more or less recover. And this is the secret that Alice and Paul share.
those it's thank the speaker. For the second half of the session, we're now going to see lattice attacks, and we will start with Amit Mukherjee will present the new memory efficient attacks on small LLMs.
Thank you. Hello everyone. So this is memory efficient attacks on small LWAs. This is a joint work with Andrew Desa, Rahul Dipman Chandrasekhar, and it is from the Technology Institute in UAE, and we three are from Indian Institute of Technology in India. So let us start by looking at our motivation to study this. So the LWE problem is one of the prime candidates for constructing post-quantum geometry, especially small maximum variant schemes like Asiacrypt hyper. So the best known attack against this kind of schemes is the hybrid attack by Nick Graham from 2007, which combines lattice reduction with some combinatorial techniques. Now, lattice reduction is not known to exploit the small maximum structure of this kind of keys. Right? So, May in Crypto 2021 provided a purely combinatorial attack that could actually exploit the small maximum structure of these keys. But the issue with this attack was that it had huge memory requirement. So he provided a numeric version of this attack in the paper and also some time memory trade-offs based on it. So we are going to improve those memoryless algorithm and time memory trade-off in this work. So let us look at our problem. So the problem so it has given you an integer q which is of size polygon n. We have an integer w, right? And we have a matrix A which is of size n cross n and whose entries are from Z3. We also have a vector P which is of length n and whose entries are again from Z3. And we satisfy this AS equal to B plus E modulo Q, right? And where this S and E are basically ternary vectors of length n and weight of S is W. So what you need to do is you have to find this S. So if you know E, then basically you know B plus E, and you can just use simple linear algebra to recover S. But we do not know E, so we can brute force it by just looking at AS minus B, and you keep on using different S until you get a ternary vector as AS minus B, and whenever you get that, you can just output that S. And since S is a vector of length n and each entry has 3 choices, so it will take at most 3 to power 10 time and this polynomial will. So for simplicity, we are going to assume that S has equal number of ones and minus one. And just for comparison purposes, for the rest of the class, we are going to fix the weight of S to be n by 2. That is, S has n by 4 many 1 and n by 4 many minus 1. Rest of it. So to understand our algorithm, we are going to do 3 basic things: a basic collision search, and then representation technique, and then the nesting technique. So let us start by looking at basic collision search. So you are given a random function f from a set finite set S to itself, and with just square root of S many evaluations of f, you can basically find y1 and y2 such that f of y1 is equal to f of y2. Right? So if you just look at this diagram, so you start with a starting point f and you keep on applying f on it. Since it's a finite set, at some point of time it has to repeat, and so you get this row kind of structure here. So you can see that this z k minus 1 and zk plus l minus 1, both of them map with zk. So basically, zk minus 1 and zk plus l minus 1 is the colliding points, right? And we can easily extend this to two random functions, f1 and f2. Now, we call the procedure row of f1 and f2 x, where x is the random starting point. And just observe that if you have a fixed x, you will always get the same colliding points. So now let us see how we are going to solve LWE using this. So this is by Van Wilgenthal from 2016. So we recall the LW identity as A is equal to B plus E modulo P. Now you just split weight in the left hand side. So you have basically n by 8 many ones and n by 8 many ones in the first vector on the left side. And on the second vector, you have n by 8 many plus ones and n by 8 many minus ones on the right hand side, and rest of everything is 0. So you just rearrange the LWE identity as AS equal to B plus E minus AS2. So now we are going to guess L coordinates, lower L coordinates of this E. Right? And this L is small enough that you can do guessing in sub-exponential time domain, right? And but this is not enough to like use linear algebra to recover the. So just note that this is a variant of this algorithm that was given by May in 2021. The original Van attack used locally sensitive hashing to bypass this getting part, but we are going to use it. So we just project this identity to the lower L bits. So we get pi L of A of S1 equal to pi L of B plus E minus A of S2. And you take the left hand side as the F1 function, the right hand side as the F2 function, and you find collisions between F1 and F2. And but there will be many collisions between F1 and F2, and only one of those collisions will actually give you the solution. So to look at the time complexity, we have to go through all the collisions. Therefore, the time number of collisions times the time needed to find one collision, and this gives you time complexity to the power 1.125, right? And now to improve this, may use the representation technique which was introduced by Harvard in 2010 in the context of subset. So just observe that the first vector on the top can be represented in 4 ways, right? So if you just add each pair of vectors, you always get this top vector. So what is the idea? So the idea is that we have to find this S, right? And previously we just split S as S1 plus S2, right? And we had to find S1 and S2 to actually recover the solution. But now we blow up the search spaces for S1 and S2, and now you have many representations of S. So you have, let's say, S1 dash plus S2 dash is also S, then S1 double dash plus S2 double dash is also S, and S1 triple dash plus S2 triple dash is also S. Now it is sufficient to find any one of these pairs. So this lets us to only examine a fraction of the total. You don't have to go through all the page, you just have to examine a fraction of it. So we are going to see how this impacts the time complexity. So now you can see that we don't go through all the collisions, but only a fraction of the collisions. Note that since the search space has gone up, so this key row should increase. But this representation actually takes care of it. Now we are going to see some concrete instantiation. So the first one is Vandikanda that we have already. Second one is maze ref 0, where you have now we have distributed the whole weight throughout the vector in both the commands, and now you can represent a 1 in the solution as 1 0 or 0 or a minus 1 in solution as 0 minus 1 minus 1, and this improves the time complexity. In maze ref 2, what he does is that he introduces some extra ones and minus ones in both the sums. So the extra ones in the first command can cancel out with extra minus one in the second command to give you zeros in the solution. Similarly, you can have extra minus one in the first solution and cancel out with extra ones to give you zeros in the second. And this further increases the number of representations and therefore improves the time complexity of the in maze ref 2, he introduces some extra 2s and minus 2, further increase the number of representation and improve this to the power 0.9. And now we are going to improve this result to the power 0.8425 and let's how we are going to do it. So we are going to use the nested collision search technique by Dinu Dunkelman from 2016, which was later adopted in the context of subset sum by Esser and May. So to do this, we split the solution in 4 halves. We have S equal to S1 plus S2 plus S3 plus S4. And using the LW identity, we just rearrange the LW identity to write it as a of a times s1 plus s is equal to b minus a times s3 plus s4 plus e. And just like previously, we now get two L coordinates of e. Note that this 2L is small enough that you can do it in some do everything in some time. So basically, you are getting out for p, and but this is sufficient to identify the solution as unique. So basically, you now project the LW identity on the lower 2L coordinates, and you get this identity. Now, to make the nesting work, we introduce an arbitrary constant r as the lower L coordinates of the left hand side. Basically, r is equal to pi L of a times s1 plus s2, right? And we just rearrange it, and we get pi L of a of s1 equal to r minus pi L of a of. You consider the left hand side to be f1 function, the right hand side to be f2 function. Similarly, from the right hand side of this identity, you get f3 function and f4 function. And now you would like to find collision between f1 f2 and f3 f2. But this is not sufficient. So what we do is we introduce two more functions, g1 and g2. Right? So g1 is basically eta L of a times y1 plus y2, where eta L is basically projection to the upper L coordinate, and this y1 is coming from a collision f1 f2. So basically, what is happening is that we are going to search between collision, search a collision between G1 and G2. And whenever G1 is called, we automatically call a collision search between F1 and F2, right? Which gives you Y1, Y2, which satisfies the corresponding identity on the lower L coordinate, which is shaded here by blue. By orange. But yeah, and whenever you call G2, you basically have collision search between F3 and F4, and like satisfies the corresponding identity on the lower L coordinate, and then you find a collision between G1 G2, and this satisfies the identity on the upper L coordinate. So all in all, you satisfy the identity on the all two L coordinates. So depicted by a picture, these smaller holes are basically the application of GI. And this is basically whenever you are calling a GI, basically you are calling a collision search between the corresponding Fi, and this large row is therefore a collision search between G1, right? And the point where this large row is intersecting itself is the point where you have matching in the lower L bit as well as the upper L. So the time complexity is same as previous. It is the total number of collisions divided by number of representations times the time needed for one collision. So just notice that since we are matching on more number of bits, this T nested is actually increasing, and since we repeat it less often, so therefore this number actually is this time complexity. So up until this point, we saw it for a fixed weight n by 2, but for a arbitrary weight, you can see that our lower one is our method, and this green one is made, and this upper is Van Wiesenthal method. You can see that our method is better than both May and Van Wiesenthal for every weight, and for the cryptography relevant, it's the difference is quite high. So up until this point, we didn't use their memory, but let's say we have some small exponential amount of memory available. So what can we do? So we use something called the parallel collision set by Osborne and Wiener from 1999. So so now just let's say that you want to find m many collisions between f1 and f2 functions, right? So it should take m times square root of s nine with no memory. But if you agree to pay m units of memory, then you can shave off that square root m factor from the time complexity, and you can do it in square root of m times s many function evaluations, right? Just notice that the maximum amount of memory that you can spend is always upper bounded by the number of needed columns. And we saw that for our optimal instantiations, this number is very small. So how we overcome this? We incorporate the BCS speedup into the time complexity formula, and then re-optimize it for every available memory, and we get this time memory curve. So this is for weight 0.5, this is for weight 0.61, this is for weight 0.68. Just notice that the smaller the weight, the steeper this curve is. So let me just conclude my talk. So we saw improved memory algorithm for ternary LWE. We saw new time memory trade-off for small exponential memory. And in the paper, what we have done is we have extended our technique for small max from 2 and 3. And also we have used techniques from information decode to improve the uniform basically with
For
So for your presentation, I have a question. Now you are using the two levels of linear search, and I want to know if you can use multiple level search, such as four levels of levels. And if you so what's the advantages and not the problem?
yes, so we have done it already. So we have tried that. It doesn't give an improvement. So to understand why it is not giving an improvement, we have to look at the exact way we are splitting basically this S, right? So we split this S. So the domains from which this S belongs, if you look at the domains, you'll understand why increasing this depth actually do not help.
Okay, okay, thank you.
Thank you very much for the talk. I'm guessing, so you give a GitHub. So you have, I'm guessing, maybe some estimator available. So we can plug some parameters and find the complexity of the attack, or
No. So this so the main aim of the study, we have basically we have done an asymptotic study. Uh, so we don't have an estimator available, but the formulas are available in the paper. Like so, one can just plug it in and just check like what is the time.
okay, thank you very much.
See, I'm not an expert in it, but we thought about it and we are still thinking that how that like nesting of this quantum thing to work. That we use half position and they will okay. Things like on yeah, I'm not sure about how nesting is going to work in.
I have one question. Can it implemented in parallel? In parallel?
In parallel?
Yes.
Yeah. Yeah, well, so yeah, okay, this is what basically parallel collision has done. So it, yeah, basically you can spend some memory to actually gain some time.
So it is mentioned that it's really a very really a really as you mentioned for band.
Yeah, I think it is similarly, but I think the currently one is the interest, so we just did it for that. And also we have done it for small maximum tools, which are used in like hybrid and
Thank you very much. So I consider that the situation that is more post. I mean, for AW with ternary errors, basically, if you, this problem becomes easy if you get like in cube samples. So have you considered like the case that whenever you get more samples?
I think
I mean, for LWE, it's ternary error. So basically, the program becomes easy if it gets like n cube samples, n cube LWE samples. So I mean, so here I guess you fix the number of samples to be like a multiple of n, something like that.
See, it's not about samples, right? So what I meant here is that this E, this error vector E. So we just want to do it like so that it doesn't affect the asymptotics, right? So we just guess only that many coordinates such that we can guess it for free. Basically, only substantial diagram. So that's why we go. And if you look at paper, you will see what is the exact value of like this figure and why we can do it for exponential.
Okay, thank you.
Any other questions? Thank you very much again for the next section. Today, I'm really very happy to have Julian explaining too many hints can break a delivery with on the other. Thanks for the introduction. So this is trying to work with Alex Mai and with Wolf. Like the previous talk, this one is also about LWE. So let me once again record the definition of the LWE problem. Given a matrix A and a vector B, both have entries modulo Q, where Q is just some integer, and B is of the form A times S plus E, where both S and E are secret and short vectors. And the task is simply to find the secret vector S. Now that Kyber and dilithium have been standardized and soon will be used in practice, it gets increasingly important to study the side channel resistance of LWE-based schemes. And there has already been quite a lot of research on that question, and one particularly interesting step in that direction was from Crypto 2020 from Daphne Solet, Picard, Bong, and OC. And they introduced a very general framework in which you analyze the security of LWE sections. They called their framework LWE with hints. And here, all side channel leaks are modeled as inner products. So more precisely, they assume that the attacker somehow managed to obtain some inner products Li, which are taken between the LWE secret S and some known vectors Vi. And you can think of inner products maybe being defined of the integers, or also as a Q would be defined, where Q was the modulus of which the LWE instance was defined. Maybe a power of 2 will also be fine. And in fact, any modulus that you would like would work. The hints defined over the integers would be called perfect hints, and the others would be called modular hints. Now you might be wondering, why is that a good model for side channel leaks? Well, in fact, almost all side channels leaks that you can think of can be modeled exactly like this, like an inner product. So for instance, a coordinate that leaks of the secret is simply an inner product with a unit vector that has zeros everywhere except in one place. In that place, you would have a 1. Or if you have a ring or module LWE, maybe an NTT coefficient leaks, then that is again an inner product with a vector that has powers of some value theta, where theta comes from ZQ. And with some creativity, you can think of many more side channel leaks which can be modeled exactly like that. And maybe it's also interesting to note or to recall how LWE encryption works. Very roughly, it works in 2 steps. First, you compute an inner product between the ciphertext C and the secret S. After that, you round the result to the closest message M. And whenever this first step leaks something, you can expect to get something that looks like an inner product. Now, the first type of leak is coordinate of S would typically be a perfect hint. An NTT coefficient would typically be a modular hint defined modular Q, right? Because the entity is also defined modular Q. This leak in the decryption probably would also give you a hint modular Q because this inner product is taken modular Q.
But maybe somehow you manage to get the leak before the modular reduction is applied in the implementation, then you might even get a perfect hint of this inner product. Maybe also your leak is not perfect, maybe you only get a few bits, like if you get the least significant bits, then you would only get a hint modular 2, or if you get the least significant bits, you would get a modular hint modular 4, and so on. So how does that work? Basically, in 2 steps. First, take the LWE problem and turn it into a lattice problem, and that's just the usual way of how you would attack LWE, so that's just the primary lattice. After that, they take the hints and now try to incorporate these hints into the lattice problem to transform it into an easier lattice. But as we might expect, the more hints you have, the easier this lattice problem is. So, some concrete numbers. For Kyber 512, if you had roughly 200 random perfect hints, then that problem would in fact become feasible. Where feasible means like you can do it on a weekend on the laptop. And if you don't have perfect hints, but maybe few modular hints, then you're 400 hints. Now, if you're a side channel analyst, that's probably good news, right? Because maybe you studied an implementation of Kyber and somehow figured out that this implementation leaks 200 random perfect hints. And then you no longer have to think about how you attack this implementation. You just take these hints, plug them into this framework, and the framework will do the attack. So it's very nice. Unfortunately, currently it only works in theory. The thing is, this transformation, which tries to integrate the hints into the lattice problem, is currently infeasible. Theoretically, it isn't. It runs in polynomial time, so that's fine. But on current software, it's just way too slow. Again, let's look at some concrete numbers. If you were to run it on a Kyber 512, or to integrate something like 30 hints, it would already run for more than 1,000 minutes. I think it was 30 hours, which it took. And that's not the actual attack, right? That's just the previous. That's the thing where we want to operate the hits into our head. So after you've done this computation, you will still have to run the attack. And if you here integrate only 30 attacks, you will still end up with an infeasible lattice problem, as I have written on the bottom of the slide. To really get a lattice problem that you can solve, you have to integrate like 200 perfect hints. And as you can extrapolate from this graph, that's currently just impossible to do in any reasonable amount of time. So what we did basically, we made this transformation efficient. And yeah. These blue dots are the runtime of our approach. So see, this is the log scale, and we have a huge gap. So for instance, for 30 hints, the old implementation took more than 1,000 minutes, and we require less than 1 minute. So because I was much more efficient, it now allows us to really go up to a large number of hints. Here, now you can see it. We can easily go up to like 200 perfect hints and get into this regime where lattice attacks really become feasible. And even for 200 hints, we already tried. I think it was half an hour. So how does our approach work? Essentially, we just get rid of the intermediate step. So in the original DDGR20 framework, they first transformed LWE into a lattice problem and then incorporated the hints. Well, why not just incorporate the hints first into the LWE problem and then turn it into hints? And that makes it very naturally much faster, because what we do is essentially just linear algebra. Linear algebra algorithms are very efficient, whereas lattice algorithms typically are kind of inefficient. They have polynomial time, but not super efficient. We do, in fact, have not one algorithm, but two. The first algorithm, I just showed you the results on the previous slide. For the first algorithm, that's very general algorithm that works for all kinds of perfect and modular hints. But we also have a second algorithm for a more restrictive setting, where we only obtain modular hints, define modular Q, and that's even more efficient. There, our implementation only runs in the order of seconds, even for cryptographically sized instances. That's of course more restrictive, but we think in practice it's maybe not too bad, this restriction, because all the operations in LWE-based schemes are performed mod Q anyway, so we think getting these mod Q hints is probably quite effective. In this talk, I will mostly focus on the algorithm one, but in the end, I'll go back to it. So let's dive right into algorithm 1. For that, to understand the algorithm, I think it makes sense to briefly recall how you would usually attack LWE using lattices. But for that, let me once again take the LWE problem, but phrase it a bit differently. So it makes sense to think of LWE as the following problem. We're given a matrix A and a vector B, and now we're asked to find some short vector S, such that minus A times S plus B is equal to some short vector E. How can we turn this into lattice? That's basically just one thing that you have to do, and that is you have to make this reduction modulo Q more explicit. So that means you're not only searching for this short vector S, but you're additionally searching for some vector W, such that you get an equation over the integers, and now we don't have just minus AS plus B equal E, but that this additional plus Q times W. And this W just is your reduction modulo Q. And this is in fact already a lattice problem. Consider the following lattice spaces. Q times an identity matrix, we have minus A, B, and then below that they are just where we have this identity matrix. And now if we multiply W, S, and 1 to this matrix, what do we get? Well, in the first line, we get Q times W minus A times S plus B times 1. And that is exactly the left-hand side of this equation, right? So by definition, the first row of the resulting vector has to be E. And figuring out the second and third component of this vector is very easy. I mean, we get identity times S, 1 times 1, so we get S. And now by definition, E and S are short vectors, and 1 is the very small integer, so this will be a quite short vector. And in fact, you can show that for typical parameters, it will likely be even the shortest vector in the studies. So attacking LWE is basically just computing the shortest vector in the lattice generated lattice. Good. Now back to LWE with hints. For simplicity, I will only talk about perfect hints, but we show in the paper that everything that I show you now also works for modular hints with some minor modifications. Okay. Say we obtain some hints, like a fixed number, let's say k. Now we use these hints to define another matrix and another vector. We have put in the hint vectors vi, and in this vector b, we just put in these elements. And then we have the following relation, that is minus a prime times s plus b prime is an all-zero vector. What is that? Well, this product here between matrix and vector simply gives us the inner product between the vi's and s. And by definition, these are equal to the li's, so minus this vector plus the li's has to be 0. And now that looks very similar to the LWE, right? It's A and A prime, we have B prime, and 0 kind of takes the role of the E. So LWE with hints is essentially the problem of satisfying two equations, the initial LWE equation and also now this equation that we did. And then we thought, well, let's just try to solve both equations at the same time. For that, maybe it's a good idea to just turn them into one equation. So maybe do something like that. Here, the first row in this equation is just the usual LWE equation. And that also very naturally gives you a lattice problem. So with a minor modification to this base matrix, we get a new lattice problem, and that is we only have this A prime and B prime to our base matrix. And if you now multiply a W and S and 1 to this base matrix, you get almost the same vector, that you still have E as at 1, but now you also get this 0 to the K. And then the new attack is maybe to just find the shortest vector in this case. And this will in fact be already a much easier lattice problem than just using the usual LWE. And that's because adding this A prime and B prime will sparsify your lattice, and the sparser a lattice is, the easier it gets to find the short vector. So that already is quite a bit of an easier problem. But we didn't stop here, because we have even some more information. We know that the vector that we search has all zeros here. So instead, let's call this space B. And then what we really want to do, we want to compute the shortest vector of the sublattice of this lattice generated by B, namely the sublattice that has only zeros in the coordinates n plus 1. because we know that the vector we're searching for lies in the sublattice. And for every hint that we have, we go into the sublattice will decrease the dimension by 1. So since we have k hints, this in the sublattice has the dimension decreased by k. And again, the smaller the dimension of a lattice, the easier it gets to find the shortest vector. So not only have we sparsify the lattice, but we also decrease the dimension. So given sufficiently many hints, it should be quite easy to recover the shortest vector of this lattice lambda hint. Okay. Now you might be wondering, okay, fine, but why should I use this? Right? There is already this framework by DDGR, and maybe they even have a better lattice. So maybe it's pointless to use ours because maybe on their lattice it's much easier. Fortunately, that's not the case. In fact, we can show that recovering the secret from our lattice is exactly as hard as recovering the secret. And what we showed here is essentially that our lattices are isomorphic. So they are isomorphic, and additionally, the geometry. Okay. At least we are not worse than the DDGR lattice, but we do in fact have an advantage. That is, computing the basis for our sublattice is very, very easy. And that was the problem that we started. Right? In the DDGR lattice, it was very expensive to even find the basis for this. In front of it, it's very easy. Let me quickly sketch how that works. So we have the lattice lambda hint, and we have the space matrix B, and now we want to compute the basis. For that, it's useful to keep in mind how large the dimensions in this matrix are. So I put them here for you. So the only thing that we really have to do is we have to find a unimodular transformation that changes the shape of our matrix to something that is something that has in this first m plus n minus k plus 1 block in the k columns here is 0. And the rest we don't have to care on. And then this will already be a basis for logic. Why is that? Well, first of all these vectors already have a 0 in the right position, right? In position n plus 1 to n plus k. That's where we're going to have the zeros. So all these basis vectors already belong to the sublattice. And as I said, every hint decreases the dimension by 1, and so we have k hints, so the dimension will be decreased by k. So this base matrix already has the right dimension. So all the vectors belong to the sublattice that we want, and it has the right dimension, so it has to be a basis. So if we were working over vector spaces, it would be very easy to transform this matrix into something that looks like this, right? We just do some kind of Gaussian elimination, and then. But since we are working over lattices, we unfortunately can't use Gaussian elimination, and so we have to do something more clever. And fortunately, that's also here with very efficient tricks. So the first observation that we made is the first m basis vectors that we have already have the desired shape. And we want to put in a 0 here, but they already have a 0. So these we don't even have to touch, we can just keep them as they are. We only have to modify this part. And that's very good, because m is at least as large as n. So what we do by ignoring this part of the matrix, we at least half the dimension. So that's very nice. So and how do we turn this thing into all zeros here? Well, basically in 2 simple steps. First, we multiply this a prime here and this b prime here by a large constant, which is exponential in n and polynomial in q. And then we simply LLL reduce the n plus 1 right. And then we will in fact get something that looks like. So why is that? So the LLL algorithm will try to find vectors that are shorter than this constant. But in our lattice, we now multiplied everything in this k-dimensional block by c. So as soon as we have a vector in this lattice that has a non-zero component here, it will be larger than c. And so the only way to find a vector that is smaller than c is to put zeros here. So we simply have to reduce it, and it guaranteed we will find something that is shorter than this, and by that it will have zeros. So this works. And since it's only an n+1 dimensional lattice, this of the second step will be reasonably efficient even for cryptographic size. Now we implemented that and also run some experiments, also for Kyber and dilithium and taugen. And then we observed some kind of interesting phenomenon, and that is if we have really a whole lot of hints, like too many hints, that's where the name from our paper actually comes from, then the second step of this algorithm will already recover the LME secret. And that's a bit strange because this isn't the attack that we're running, right? This is just the pre-processing. Initially, we first want to do this, and after that, want to run the attack. But apparently, there is a regime when you have really a whole lot of hints, then you don't need the attack. And the pre-processing will already give you the LMEs. Let me show you some concrete numbers. For 512, 512, 568, and this thing 4. For instance, for Kyber, if you have a bit more than 230 hints, then runtime basis construction really takes quite a bit of time, like 3 hours, but still it's very reasonably efficient. And then you just do the basis construction and you don't have to do the attack. Basis construction will immediately give you the secret. For Falcon, it's very similar, even one hint less, and again, after 3 hours, you get that secret. For larger parameters, as you would expect, you need more hints, that also takes quite a bit more time. But even for the lithium, we can still do it in a week. And we found that quite surprising that it still works so well. Because the lattice that you have in the lithium are dimension 2048 or 49 even. And that's really already at the gap what current software can currently even handle. And it still works in just a week. What we also found kind of interesting is we now take the number of hints and divide it by the LWE dimension. They are all kind of similar, all something between 45 and 61%. Yeah, but we're not so sure that it's will asymptotically also true that it's always roughly 1/2 or just because the parameters of these schemes are chosen as they are. But at the beginning, I said that we also have a second algorithm that works on Q modular hints. I would also like to show you some results of that. So here it's kind of the opposite. Here the basis construction runtime is basically nothing, right, because the algorithm is so efficient. But here we don't have this phenomenon that the algorithm will recover the secret on its own. Instead, we still have to run the attack afterwards, but as you can see, that is still very efficient. Like even for the largest thing that we consider for the lithium is less than a day, so only 10 hours. Of course, that not only works in this too many hints regime where LLL already breaks LME, or maybe I should have said, like here, this is again the amount of hints that you need to have to be able to break LME using just LLL. But if you have quite a bit less hints than that, then you have to use stronger lattice reduction, like BKZ, and then everything still works, you just have to spend more time. For instance, here are some more results for Kyber 512, where we first did the pre-processing, and in a regime where the pre-processing does not find the secret, instead we afterwards still have to run some low block size PKZ after that. And you can see even for only 200 hints, you can still do it in roughly 9 hours. So that already concludes my talk. So let me quickly summarize. What did we do? We introduced a novel approach for LW hints. We can finally efficiently construct lattice spaces and finally push the DDGR framework into the real world. Our algorithms are particularly efficient if we only have these Q modular hints, which we think are probably quite relevant. And probably that's also very important. Our bases have the exact same quality as the original DDGR basis, so you have no disadvantage when using our implementation. We also have made our implementation open source. It's available in GitHub and written in Python. Right. So let me end with one open problem. In the original framework, they have one more class of hints called so-called approximate hints. And here you don't learn these inner products not exactly, but only get approximations. And conceptually, they work very differently from the modular and perfect hints, and we weren't able to make this transformation efficient. think would be very interesting to also do that. Thank you for your attention. You will next look at the question. Thanks for the nice talk and very nice work. And I'm wondering, how did you sample the hints when you did the experiment? Yeah. In both settings, perfect and modular hints, we just took random hints with random entries between 0 and Q. Okay, thanks. And for the modular hint setting, it really doesn't matter. The distribution of the hints doesn't matter. Regardless of what hints you have, you will always get these results. But in the perfect hint setting, it depends on the distribution. Like if they have coefficients from an even larger set, then you will need even less hints than that. But if they come from a very sparse set, then you will need more hints.
Thanks for the nice talk. You actually know why LFL is a solution?
No, we're quite puzzled about that. We tried to prove it like using Gaussian heuristic and the usual estimates, but it doesn't match.
Actually, have the same thing in the side chart.
Mm-hmm.
Some years ago,
Mm-hmm. Yeah, I don't know what's going on. The theory that we have doesn't match.
Hi, I have a question about the last open problem that you mentioned about integrating the approximate hints.
Yeah.
I was wondering if that means that with your approach, if you have this kind of hints, then just disregard them, like discard them, or whether you can do the transformation that you showed and then like use the old approach of the new LLP.
Yeah, right. If you have all types of hints like perfect hints and modular, then you can first do our stuff or the perfect and modular stuff, and then afterwards do the FP. And that will probably be more efficient because we decrease the dimension, and then this could maybe be the original implementation.
Cool, thanks.
Yeah, I was so you only consider the bipolar type analysis.
Yes.
Will it make sense to also look into the dual type or
yeah, I think so that something similar should work for the dual attack, but probably one should wait before the motion and the dual attack is settled.
Yeah. Yes, technical story. I was wondering the bounds you showed of the you were all informed.
Yeah. Yeah,
every was it like 7 days.
Yeah, we did I think 32 experimental per scheme on this.
Hello. I want to ask a question. I want to ask, what is the difficulty of your approach to deal with the approximation hints?
With these perfect and with the perfect hint, it's mainly going to a sublattice, and with these modular hints, it's specification of the sublattice. But for the approximate hints, it's a distortion of the sublattice. And this distortion seems to always require some matrix inversion of rational matrices, and that seems to be just kind of expensive.
Okay, thank you.
I'm interested in your abstraction for creating.
Yeah. This one or the
this one.
Yeah.
And actually, we proposed that solve the figure problem before, and we used the formula also I can define directly use the dimension as an approach.
Like using the Herman normal form instead?
Yes. and coefficient of the vector would give me the coefficient
Do you think computing the Hermit normal form of this lattice or like a larger lattice? Well, no, we didn't try that. What we did try was this standard approach where you take the lattice and then the base for the lattice that you want to intersect it with. So you blow up the lattice dimension, and if you then compute the Hermit normal form, then you will get the base of the intersection. But that was very inefficient because then the lattice. I don't know what will happen if we just compute the Hermit normal form here. We did try that. Could be. I mean, well, I'm not entirely sure because technically, I think the theoretical runtime of LLL and HNF is kind of similar, right? But I think we have much better software for LLL than HNF. In practice, this will.
Page 8 of the so you mentioned your long PTC, low blocks.
This is?
Says low blocks.
I don't remember, but it's in the paper. If you, I can log it up just after the talk, and then I can.
So I want to say the page 7.
7?
Yeah, page 7.
Yeah.
Yeah, I noticed that you I see and then do the LLL reduce to get the zero counts. And have you ever considered the of them to compute the kernel of matrix? Yeah, the target is to get some zero matrix. Right.
But the kernel over which field? I mean, we're not on the field, right?
Here just got maybe K. The dimension you press to get the then plus K.
Yeah, but if I want to complete the kernel, I just have to specify the kernel over which field. So like, do I want to do it on a final field or maybe the rationals or maybe fields? And here it has to be just basically all the integrate.
I have a question that intuitively, of course, as we have more things, we can solve the complication. But I want to in practice, what happening? How can we get how it is reasonable person that we can have the instruction of that and also yeah, moreover we can with the function more stronger and with more and more things and I mean if it's reasonable to fit the function.
I think especially for these things are very again, most such analytics typically target the coordinates of the secret.
Actually, my question. So yes. Did you try your approach on standard preferences, which are based in the computer delivery? So, are you able to the same amount of things in measure from here to break standard delivery of the same dimension? Yeah. Okay.
We also tried both modular and
and so LLL is also overperformed for regular intervention. No one answered the question. Then we can thank the speaker again.